try this example from the book. Try to cover up the explanation a little bit and just look at the example here.
Do we know what the safety standard was?
I think they told you that in the problem, yes.
Oh, okay. So then, so this is using n equals.
And you can use this table.
So I can use half-life then?
Because the table gives us half-lives.
You're solving for T.
Right. Good. It's always good to label the question with a question mark.
So n is equal to 2,900 and n is 185.
Let's try labeling our graph over here. So what does this point represent here? What's the number for that point?
The original.
Yeah, what number is that in this problem?
100. So
I think we're getting a little confused by what we mean by original here. Now, of course, originally, radioactivity was very low, because before the explosion, there was no radioactivity at all. Or before the explosion, the radioactivity probably looked like this, close to zero. But what we want to know is the original number of nuclei originally, immediately after the explosion.
then that would be 2,900.
Right, this number here would be the 2,900. And then what was the other number they gave us?
185.
Which you can see is far lower. 185. And in terms of this graph, what they want us to figure out is this point on the horizontal axis. They want to figure out how much time does it take to get down to 185. Now, what variable would we use for 2,900 and what variable would we use for 185?
2,900 is n.
And 185?
And not.
What does n naught stand for again in words?
The number of particles after a certain time t.
That's what n stands for.
Oh, sorry.
N naught is the original.
Original.
O is for original here.
Yeah.
N0 is for the original or starting. But we have to be careful by what we mean by original again. We don't mean the number of particles at the dawn of time or in the Garden of Eden. We mean the original number of particles immediately after the explosion. N sub 0 here. So this would be n sub 0. And this would be n. So it looks like the main problem we've been having so far with this problem is correctly assigning the n sub 0 and the n. Well, one way you can tell the difference between them is who's always bigger, n or n sub 0?
N sub 0.
Yeah, n sub 0 is always bigger because n sub 0 is always this maximum original amount. The number of nuclei can only decline from here because this is decay. So just as a trick for assigning these correctly, this number has to always be the bigger number, and this number has to always be the smaller number. Otherwise, we've made a mistake.
So then it would and the half-life is 8.04.
You simply looked up in the table that the half-life was 8.04. Good.
So then
what's the next thing you're going to do?
I was going to simplify it.
By doing what?
Dividing 2900.
That sounds good.
So 0.06.
Let's get one more decimal point. Let's call that 0.064. That's a good instinct. We might as well divide these two numbers into each other. 185 divided by 2900 to simplify the equation.
And then take the log of both sides.
How do we know we have to take the log? Because we got another situation with a variable and an exponent. It always helps to take the log to get rid of a variable and an exponent.
Log of 0.064 is negative 1.19. And that's equal to negative t times log of,
Oh, so did you decide to take the regular log or the natural log? It looks like here you took the regular log. Here you can take either one you want. However, since we took the natural log in the previous problem, maybe we'll just stick with natural logs. You could do either one, but I already wrote natural log on the board, so we'll take the natural log.
so that's negative 2.75.
Right. You're right, it doesn't matter. As long as you're consistent, you could use either the regular log or the natural log. But maybe we'll just get in the habit of always using natural log for these problems. That will always work.
So negative 2.75 equals negative t over 8.04 times ln of 2.
That's right. The whole beauty of taking the natural log is it brings the exponent down. Now we've got the variable out of the exponent.
So I would divide by ln of 2.
That's right.
And I would get negative 3.97.
Mm-hmm.
And then solve for t, so that times 8.04. So equals negative 31.88 equals negative t, so t equals 31.88. Days.
How do we know days? Because the table gave us the half-life in days. Good. What we figured out was this point here. How much time has to pass on this horizontal axis to get us down to this low level of radioactivity from this high level of radioactivity? Good.
So they ask for it. Okay, I got you.
So they rounded up to 32.
Yeah.
Good. All right, well, this is the example I was just talking about, the nuclear accident in Chernobyl. There was fallout from this iodine-131. Originally, the iodine levels in Romania, which is not Ukraine, but it was still in the fallout range, the iodine levels were way up here at 2900 when they were supposed to be down at 185. And so it's a very practical issue to figure out how long it takes for radioactivity to get down to what they thought were the safe levels. Actually, this wasn't too bad, just 32 days. All right, I guess it was not so great if you were actually there at the time. So we've got these numbers here. So what were the issues that came up here? Well, now we have two ways to solve these types of problems. We can use the lambda equation or we can use the half-life equation. How do you know which one to use? Well, you use whichever one is convenient based on the information you were given. If you're given the half-life, you should use the half-life equation. And if you're given lambda, you should use the lambda equation. In the textbook, they have a whole table with half-lives. So it was convenient here to use the half-lives. If you go back in your notes, the problem we did before this was about the same situation. It was about iodine 131, but for that problem, I told you what lambda was. Well, since I told you what lambda was for the previous problem, it was convenient to use the lambda equation. But in this case, well, you could still have used that lambda that I gave you for the previous problem. You didn't have to use the half-life equation here. If you just went back in your notes, we already have in our notes from the previous problem what the lambda is. And so you could have used lambda. But they wanted us to do it with the half-life, because that's what they have in the table here. So we need both of these equations in our cheat sheet.